This unit focused on linear and quadratic equations, but we didn't define those concepts and then do a full development of them. Instead, following the style of this course, we gave just a few problems, and we hope that those allowed you to dig into the ideas, play around with them, have some fun for some summer math, but also maybe see linear and quadratic equations from a slightly different perspective than you're maybe used to, or than maybe the most common angles are for taking on these concepts. In the first task, our goal was to focus on rate of change and to really think about rate of change as a relationship between quantities that are varying. And so in particular, there were these quantities of the points scored in a game, and then the other quantity being the average points per game, and really thinking about how one relates to the other in a dynamic way, and making some complex comparisons and things like that. This is different than the normal approach to slope, where a lot of students come to think of slope as a static characteristic of a line. So if you have a line, and for instance like a graphed line, slope is this characteristic of its steepness, and that is more of affixing a kind of a static characteristic rather than a dynamic relationship between two different quantities. The other way that students very often think of slope, this is probably even more common, is they think of slope as just one component of a linear equation. But again, it's kind of thinking of that one piece as the slope rather than thinking about slope in this dynamic rate of change relationship way. So hopefully you were able to, with this task, have some fun thinking about Jordan's rate of change and how for him, each point that he scores in that last game gives him 1/82nd more of a point per game in his average. And then for Shaq, it's 1/60th. So for every point that he scores in the final game, he gets another 1/60th of a point per game into his average. So those slopes or those rate of changes are different, and you can bring in some knowledge of fractions here and think about how Shaq is actually getting more value onto his average for every point that he scores compared to Jordan. So that means Shaq will eventually be able to catch up, and even if Shaq scores less, he might be able to actually overtake Jordan because his points are worth more. All those dynamics. We hope that you had fun kind of coordinating that information and thinking about those two rates of change together. And hopefully you found also that graphs can be very helpful to look at those complex relationships and look at the different scenarios of when Jordan wins and Shaq wins. Math Task 2 dealt more with quadratic equations, and here we wanted to focus on creating a quadratic equation from a graph, because most problems typically involve creating a graph once you've already been given an equation or written an equation. We also wanted to have it be a graph that involves points that are not the intercepts or the vertex point, but using these other sort of semi-random points rather than the special points, but still have to come up with a quadratic equation. We also then kind of push a little bit further in task 2 to explore the uniqueness of the quadratic equation. So can there be more than one quadratic equation whose graph goes through two particular points? This idea of uniqueness, especially uniqueness of different polynomials through points, is going to come up again in Unit 3. Now, the main thing that we want to do with these concluding math videos is to just share one or two additional mathematical ideas that connect to the things you were working on, but these ideas you're not actually responsible for solving or turning in. It's just something that we think is worth sharing. So first we're going to mention something about linear equations, and then we'll finish up with a comment or two about quadratic equations. There are several forms of linear equations, and I'm sure you're very familiar with them, but we want to throw one more in the mix that you might not be as familiar with. But we'll start with the champion slope-intercept form. Students usually very much prefer this one, and it does work well if you have slope and the intercept, and it's easy to identify the slope and the intercept. There's also the point-slope form, and then that connects very closely with just the definition of slope. But the definition of slope is another way to actually represent the relationship between a varying x and a varying y. Then there's also the standard form, which is nice because it can handle vertical lines in addition to the horizontal and oblique lines. The other one that we want to throw in here is one that I kind of think of as the transformational form. I'm not sure if that's a technical name for it, but here it is. And what I think this one is really nice for is to make connections to other lessons that you might do on transformations, even geometry lessons, but definitely also lessons with other algebraic functions, where you work with some kind of stretching or shrinking this factor here, the horizontal shift happening inside parentheses, and then a vertical shift happening outside parentheses. This is a way to think about all lines as just being a transformation of the parent function y equals x. So you can take y equals x, you can then stretch it or shrink it to change the slope, and then you can move it anywhere you want in the coordinate plane. And then it takes this point x naught, y naught, and it makes it the new location of the origin. So you could think of it as just any point on the line, but you could also think of it as, oh, that's the origin after we've shifted it horizontally and then shifted it vertically. So that's kind of nice. I think what this can do is it can allow you to connect to the two big important ideas that really should undercut all of these representations or all these forms of the equation. The big thing is that students think about linear relationships between varying quantities, and they can think about transformations. What we don't want is for students to think about these as 5 completely separate things that they need to memorize, or 5 different equations where they have to try to read their teacher's mind for which one they're supposed to use. Really, we want them to see the structure underneath all of these. Finally, we just want to make a few comments about the quadratic formula. So you all know the quadratic formula. Lots of students have memorized the quadratic formula, but we want to look at it in a slightly different way. Now, the way that you know it and the way that students know it is not the way that it was always written. If you look back in textbooks 70, 80 years ago, they wrote it in a variety of ways, and it's just more recently that we've kind of standardized this way of writing it, at least in the US. But we have this fraction here, so we can rewrite it in some different ways, and the way that we want to look at it is to actually break the fraction apart into negative b over 2a plus or minus the square root piece over 2a. And this whole segment that's after the plus or minus, I'm just going to refer to that with a star just for ease of communication. But this new way of writing it is clearly equivalent, but it allows you to see some different things. First of all, you can see the symmetry of quadratics and the symmetry of parabolas, because we have this negative b over 2a, and then we have the same amount to the left and the same amount to the right. And so what that means specifically is that the leftmost root is going to be the star distance to the left, and the rightmost root is going to be that same star distance to the right, and right in the middle then is the negative b over 2a. By symmetry, that must be the line x equals negative b over 2a along which the vertex rests. So we can see the roots are symmetrical about the vertex. The last thing we wanted to mention was just some relationships between the roots of a quadratic and the coefficients of the general form ax squared plus bx plus c. So if you have the roots r1 and r2, then the sum of the roots is actually negative b over a, and the product of the roots is just c over a. So that actually works out pretty nicely. If you want to try to prove these relationships and you know the quadratic formula, or if you can already assume the quadratic formula to be true, then you can prove it by using this form that we were just talking about, which you can treat as a binomial and multiply it out, and things cancel very nicely. So you have the roots here, and you can find that the sum is negative b over a, and you can find that if you take these two roots and multiply, the plus version and the minus version, multiply them together, everything cancels out nicely to get c over a. You can do that on your own if you're interested. Even if you have not yet established the quadratic formula, you can prove these relationships by just taking the standard form ax squared plus bx plus c equals 0, and then take the linear factors form, so x minus r1 and x minus r2 equals 0. If you just rewrite each of those a little bit, you'll find out that what shows up as the linear term is negative b over a in the first one, and what shows up as the linear term is r1 plus r2 in the second one. And then what shows up as the constant term is c over a in the first one, and it's the product r1 times r2 in the second one. So these relationships are nice because this way, if you know the roots, you can then just take those roots and use that to generate the coefficients, right? You can add them to get your b coefficient, you can multiply them to get your c coefficient, and you can just have a be 1. Or if you don't know the roots, but if you know the coefficients, and if you happen to be working just in the integers, you can then find out a list of possible roots. And this happens actually a lot with students where they have to find these lists of possible roots, but usually it's very procedural and they don't really know why it works. But where it comes from is just noticing this relationship between the roots and the coefficients.